Somewhere tonight, a telescope will collect more data than every astronomer in history could review in a lifetime, and a human being will not be the one who finds what's hiding in it. An algorithm will find it first. This isn't a prediction. It already happened. 5 separate times, this year alone. This is the story of how astronomy quietly stopped being a science that machines help and became the first science that machines are partners in. I've spent months tracking these discoveries one at a time. Strung together, they say something the individual headlines don't. Let's decode it. Start with Kepler 90I. NASA's Kepler telescope stared at the star system for years. Human astronomers combed through the data by hand, the way astronomers always had, and they found 7 planets. Textbook work. Then, in a project most people never heard about, researchers pointed a neural network at the same already studied data, not new observations, the same numbers humans had already gone through, and it found an 8th planet. Kepler 90I had been sitting in plain sight the entire time, not hidden by distance, hidden by volume. There was too much data, and the signal was too faint for a human eye to reliably catch every time. Here's the part I want you to sit with. This wasn't an AI exploring the unknown. It was an AI finding something we already had and simply hadn't seen. That distinction matters more than it sounds like it should. It means the bottleneck in modern astronomy isn't the telescopes anymore. It's attention. And attention is exactly the thing a machine doesn't run out of. That single discovery, one overlooked planet in one overlooked dataset, is the seed of everything else in this video. Once you see the pattern once, you start seeing it everywhere. Scale that same idea up. For years, Kepler and its successor, TESS, watched millions of stars, recording every flicker of starlight. Buried in that ocean of light curves were tiny, repeating dips, the shadow of a world crossing in front of its star. Too faint, too numerous for any human team to catch every single one. So researchers trained a model, call it a more advanced cousin of the one that found Kepler 90I, and it rescanned the archives, signal by signal. It surfaced over 100 planets we'd completely missed. Some are small, some are rocky. A few sit inside the habitable zone, the narrow band around a star where liquid water could exist. 100 planets, not newly observed, newly noticed in data that had been sitting on hard drives for years. And here's what actually keeps me up at night about that number. If 100 planets were hiding in data we already had, in a data set scientists had already combed through by hand, how many more are sitting in archives we haven't rerun yet? I don't think 100 is the interesting number. I think the interesting number is how many data sets we haven't rechecked. The next Earth might already be sitting in a folder somewhere in a discovery nobody's made yet. Not because we haven't looked hard enough, but because we haven't looked with the right kind of attention. Every single night, the sky is full of explosions, dying stars detonating across the universe, supernovae flaring and fading in hours. The problem was never that these events are rare. The problem is they're buried in millions of false alarms, satellite glints, cosmic ray hits, camera noise, streaks. For decades, astronomers sorted through that noise by hand, and by their own admission, missed most of what was actually there. Then, a team at Oxford built a system to do the hunting instead. It learned what a genuine supernova looks like inside a sea of garbage data, and it now catches real explosions in seconds, cutting the manual workload by roughly 85%. That's not a minor efficiency gain. That's the difference between we saw it 3 days late and we saw it while it was still happening. Speed matters enormously here because a dying star doesn't wait for a grant committee to approve a follow-up observation. The faster you catch the flash, the more you learn before the light fades for good. This is a genuinely new capability. It didn't exist 10 years ago. It exists now, and it's already running tonight. On telescopes pointed at the sky as you watch this. The universe has always been dying and being born in real time. We just finally built something fast enough to watch it happen. Now widen the lens from watching to listening. Fast radio bursts are among the strangest signals in astronomy. Millisecond-long flashes of radio energy that release as much power as the sun does in days, arriving from galaxies billions of light years away. Nobody fully agrees on what causes most of them. A leading suspect is magnetars, ultra-dense, hypermagnetized dead stars, but that's a leading theory, not a settled answer. What has changed is our ability to catch them at all. Breakthrough. Listen, working with NVIDIA, deployed an AI system on the Allen telescope array that scans for these bursts roughly 600 times faster than the previous approach. 600 times isn't an upgrade. It's a different category of listening. It means a machine can now monitor the radio hiss of an entire galaxy continuously for signals a human team could only have sampled. Here's the detail buried under the fast radio burst headline. This same infrastructure is also the best tool we've built to search for something artificial. It doesn't know the difference between a natural signal and a message. It just listens for anything that isn't noise. That's not a small side effect. That might be the actual headline. In 2025, the Vera Rubin Observatory opened its dome for the first time and captured roughly 10 million galaxies in a single night of first light imaging. It's now running a 10-year survey aiming for tens of billions. That number alone is the kind of wow statistic this channel usually leads with, but the number isn't actually the story. The story is what happens after the image is taken. A single Rubin image generates a fire hose of alerts. Every pixel that changed since the last time the telescope looked at that patch of sky. Asteroids, supernovae, variable stars, something new. At that volume, there is no team of humans large enough to triage it in real time. So an AI pipeline does the first pass, cutting the alert triage workload by a figure researchers themselves put at roughly 85%. A machine now decides, within seconds, which of 10 million nightly changes in the sky are worth a human astronomer's time, not a support tool anymore, but a gatekeeper. The entire modern survey astronomy pipeline, Rubin included, would be operationally impossible without it. Not slower, impossible. That's the quiet part nobody says out loud. We didn't just add AI to astronomy. For surveys at this scale, we built astronomy that structurally requires it. One more thread, and then the steel man I owe you. Dark matter makes up most of the universe's mass and emits no light at all. We only know it exists because it bends light from galaxies behind it. Scientists trained an AI on that bending across millions of images, and it produced the most detailed dark matter map ever built. Filaments and clumps across the cosmic web, made visible for the first time not by seeing them, but by inferring them at a scale no human team could compute by hand. Here's the steel man, because I think you should hear the strongest version of the counterargument, not a straw man of it. Skeptics have a real point. An AI only finds what we teach it to look for. Every discovery here, Kepler 90I, the 100 hidden planets, the dark matter map, came from a model trained on human-labeled examples. These are fast, tireless pattern matchers, not autonomous engines dreaming up new physics. If something genuinely novel doesn't resemble the training set, We don't know whether the AI would catch it or quietly file it as noise. I want to answer that, Steelman, honestly, not dismiss it. And I think the best answer isn't from astronomy at all. It's from biology, and it's the single clearest proof that AI-assisted science isn't a niche trick, it's a Nobel-grade method. For 50 years, predicting a protein's three-dimensional shape from its raw sequence was one of biology's most stubborn open problems, solved, when it was solved at all, one structure at a time by hand over months. An AI system called AlphaFold learned the underlying patterns and started predicting structures in days instead of months. In 2024, the scientists behind it won the Nobel Prize in Chemistry. Not a technology award, not an innovation prize. Science's highest honor for a discovery an AI made possible. And here's my honest answer to the skeptic from a minute ago. You're right that the AI didn't invent a new kind of physics or biology out of nothing, but I think that objection quietly moves the goalpost. The bar was never, can a machine dream up an idea no human ever conceived? The bar is, can it solve a problem that has defeated trained humans for 50 years? AlphaFold cleared that bar in the real world in front of a Nobel committee, not in a thought experiment. That's not a caveat on the thesis. That's the proof of it. So here's the thesis, stated plainly the way I should have stated it at the start. Astronomy has quietly become the first science conducted in partnership with machines, not replaced by them, not merely assisted by them, but structurally dependent on them at the scales we now operate at. A planet hiding in old data, 100 more behind it, a supernova caught in seconds instead of days, an entire galaxy's radio hiss, listened to at once, 10 million galaxies triaged in a night. Mass we can't see mapped anyway, and the same method in a different field entirely, clearing biology's highest bar and taking home its highest prize. None of these headlines, taken one at a time, look like a revolution. Strung together, they're hard to read as anything else. The telescopes didn't get bigger overnight. Our attention did, because for the first time, it doesn't run out. I don't know exactly where this goes next. I don't think anyone fully does. But I know what to watch for, and now, so do you. Keep decoding.